Ooh, okay. All right. I had some great feedback about using a marker, using a pen is hard to see. So I appreciate that feedback. And as I'm able to, I can pop up and replace those videos. So I have a PowerPoint presentation called Colligative Properties. And for this first video, we're going to do the first 2 slides. So there's an intro slide, and then the next slide is the Hoff factor. Then I'll have a few other shorter videos for the other slides. Okay, so let's talk about colligative properties. Colligative, I don't even know what that word means. In normal human speak, civilians, as I call them, non-scientists. But basically, physical properties that can be altered when you add impurities, when you add particles. And what's special about colligative properties is that the magnitude of the change in the physical properties is based on how many particles, but not what kind. Not if they're polar or non-polar. It's just how many particles. And basically, that's because the number of particles depends, or the number of solvent molecules that interact with each particle depends on, again, how many particles and not necessarily what kind. So that's our definition of colligative properties, our physical properties that are altered and the magnitude or amount depends on the number of particles, and these could be atoms, or they could be molecules, or they could, did I say atoms yet? Ions, atoms, or molecules. The number of particles, but not the type of particle. So what that means is if you have a liter of water, and whether you add 1 mole of, let's say, carbon atoms, or if you add 1 mole of ions, potassium, chloride, any ions, doesn't matter what charge, could be 2 plus 2 minus, just how many ions. So a mole of any ions, or if you added 1 mole of, I think it's C11H22O12, I think that's table sugar. I had a typo today. Whether it's a molecule, whether it's ions, charged particles, or whether it's neutral atoms, if the amount is the same, the change in boiling point, freezing point, osmotic pressure will be the same for each of these solutions. So however that changes the freezing point by 6 degrees, 2 degrees, whatever it is, will be the same as that one. And they will be the same as that one. So the freezing point of all of these solutions will be the same because the amount. Now, technically, there might be a little bit issue if a mole isn't totally soluble in 1 liter. It should be, but you know, if there's something funky going on. But in general, the same amount of particles gives the same change to all those colligative properties. Okay, so that's just kind of a general introduction. Now let's talk about particles, because when some particles dissolve, they don't break apart into pieces. Let me go to our next slide. Go to that one. All right, so it did an autocorrect. If you ever try to swear on a text message, sometimes it'll autocorrect. What the fork? kind of fun. Okay, the Van Hoff factor, I call it the ion factor. The reason is because it only really applies to ions. So I is how many pieces or particles something breaks into or splits apart into when it dissolves in whatever solvent it's soluble in, into when it dissolves. Okay, so this is going to be I equal 1 for soluble molecules. So molecules can be polar or nonpolar. If they dissolve in a solvent, that means like dissolves like. A soluble molecule would be a polar molecule in a polar solvent or a nonpolar molecule in a nonpolar solvent. So I is 1 because it doesn't break apart. It means every molecule stays, let's say, whole. It doesn't break apart. The way the water molecules are arranged around it is determined by the polarity, if it's a polar molecule. But it doesn't break apart into pieces. I is also going to be 1 for anything that is insoluble. It's not going to break apart into pieces. But if it's an ionic compound, I will be greater than 1 if we have a soluble ionic compound. These are often called electrolytes. Okay, so how do we figure out what is I? Well, if we have a salt like sodium chloride, which is soluble in water, it breaks apart into 2 ions, so I equals 2. So we had a group assignment where you were asked how many moles of ions. And that conversion step between 1 mole, this would be 1 mole of compound, and 1 plus 1 is 2 moles of ions. Okay, let's look at another example. Let's do sodium sulfide. That one's in the slide. We get 2 sodium ions. Remember, this subscript becomes the coefficient unless it's a polyatomic ion. Okay, and the reason it's 2 is because sodium's a +1 and sulfide is a -1. Okay, let's do one with a polyatomic ion. Let's do a big one. All right, so this is soluble, and these also have aqueous after them. I'm just feeling a little lazy today. 3 potassium ions. We need charge balance, and then 1 phosphite. So that's a 3-. That's why we need 3 positive potassium ions, because K is just a +1. And the charges have to add up to 0. I know that because there's no charge here. This itself is a neutral ionic compound. Okay, so this means I have 3 potassium ions plus 1 phosphite. So that means I have 4 ions for every 1. CPD is my shorthand for compound. So that means I equals 4. Okay, so that's it. No weird tricks. There is a Kahoot. You can click on, or you can copy and paste this into your browser, and you can, after the video, you can try that and you can practice and you can play it as many times as you want. If for some reason it doesn't give you access, just shoot me an email or a message on Canvas. All right, so that's an introduction to colligative properties and the Van Hoff factor.